up where we left off on Monday. Continuous cooling transformation diagram. So the only change here, we showed the curve that a continuous cooling, a steady cooling rate will produce a curved line as such on our TTC diagrams. And so when we have a continuous cooling situation, the nose of that curve shifts a little bit toward the right. And of course we saw at this point the reason that we deal with this idea of instantaneous temperature changes in isothermal holes, because predicting microstructure is much easier if we make that assumption. It's not always true. Sometimes we have a steady cooling rate, like an air cooler, a furnace cooler, a water quench. We talked about martensite formation, that when we quench, we don't allow diffusion to happen. So we're going to form this martensite diffusionless transformation. It's a non-equilibrium phase. So it's a completely different phase. Structure, body center tetragonal, and chemistry, some composition of carbon in there. Okay, carbon trapped into the lattice. And we'll see as we go through today, we're going to talk about metallurgy and processing of metals in a more broad term, not just steel, not just this one type of metal. What we'll see is that when we quench something, what we're doing effectively, if we're not having one of these, we call them martensitic transformations, all that means is diffusionless. And so lots of materials can have a martensitic transformation, this diffusionless transformation from one phase to another. But if we don't have that, then what we're doing is quenching the microstructure in. So whatever microstructure we have at the start of our quench, we're pretty much keeping that microstructure. And we'll see how that plays out with non-ferrous alloys. It's very important. But with martensite, what we end up wanting, so if you think of martensite, okay, it's a very brittle phase. Right? It has properties very akin to those of a ceramic. Do we generally want to use steel that's like that? No. Why do we use ceramics? So kind of a preview. What are some things that we use ceramic materials for? Yes? I can't hear you.
Oh, we can keep them on.
They have high melting temperatures. Okay, so tempered plain martensite, still lower melting temperature than most ceramics. Why else do we like them? They're hard, so sometimes we'll use them for tool bits or things like that. But even then, do we want a saw blade made completely out of silicon carbide? Why? Why do we put the tip? Why do we coat the tips in silicon carbide? So for the wear properties, we want those good wear properties, but we only use it on the tips, on the surface. Why not the whole thing? It would be too brittle. There's no toughness there. It would be very easy to break that saw blade. And I'm not very nice with my saw blades in the lab, so that could be a problem. So all of the things that we like about ceramics, some of those martensite would have, but some of those properties it doesn't have. It doesn't have the same high melting point like a silicon carbide or a silica. It isn't electrically or thermally insulating, which is something else we like about ceramics. We'll talk about that because that's our next unit. So basically, martensite all by itself, and not really what we're looking for. Okay, if we form martensite, it's so that we can temper that microstructure. And so when we temper it, we heat it up, and we're not going to talk about rates for this, but we heat it up for a while, and we allow diffusion to happen again. And so what we're going to have now is the phases that want to be present will be present, alpha and Schumann type, but are they going to form a eutectic microconstituent? Are they going to form that lamellae or even that bainite? No. And the reason is, when we have those lamellae, that eutectic equilibrium microconstituent, that forms because alpha and beta are forming at the same time from a different phase. Okay? So there's, again, that symbiotic relationship that as a little bit of alpha forms, it's shooing out, sweeping out the carbon, so now it's easier for the beta to form right next to it. So that's something specific to a eutectic or eutectoid transformation that happens slowly enough. Does that make sense? So in equilibrium, if we're cooling it slowly, allowing these things to happen at their equilibrium concentrations, then we will form that equilibrium microconstituent. Not going to happen with a tempered martensite because diffusion isn't that high and we've already got this phase there. So alpha and beta are going to form, but they're going to form, what's going to form is little tiny bits of cementite. Little tiny pieces of cementite. And what we have now is a beautifully precipitation hardened material. Very, very fine dispersion of very hard particles in a very ductile matrix. The best of both worlds. And so this is a tempered martensite. And so this is an electron, an SEM image. Okay. So, and it's a secondary electron image. And so you can see that entire, those precipitates are on the order of tens to hundreds of nanometers. Okay, you can see these tiny, tiny ones there. So this is 9 microns. So that right there, maybe a little bit more than that. That is 1 micron or less, that little rectangle. Okay. 1 micron is how many nanometers? Somebody here knows it. It's 1,000. Okay, nano is 10 to the negative 9, a millionth, a micron, or a billionth, sorry. Micron is 10 to the negative 6, micrometer. So you guys know when I say micron, what I mean? Okay. So divide that into 100, and you'd have, you can see some of these tiniest particles. We could fit almost 100 in there, in that length. So tens to hundreds of nanometers. Very, very small, very fine dispersion. Why do they want to form roughly spherical, roughly equiaxed particles? Reduces the total free energy. Okay, so this is something that would come up in phase transformations or thermo for those of you guys who are taking those classes as welding and materials engineers. But the energy, the free energy goes down as the volume goes up. Okay, so the energy of the system is going to go down as the volume of these precipitates goes up because it wants to be in its equilibrium phase. You're not going to be tested on this, so just pay attention for your own edification later on. The free energy is going to go up as the surface area goes up. Okay? So the point there is, anytime we create a surface, there's an energy with that surface. Okay, remember that was the reason for grain growth. Why were grains going to grow? If we allowed them to diffuse, they were going to grow to reduce the energy of the system. It's kind of the standard, I don't know what to answer, so I'm just, like engineers, we have fun. I don't know what the heck, I'm just going to BS on this test answers. Like, why does this happen? Why did, just dare to try it on like a history test. Like, why did such and such happen in such and such point in history? I can't think of anything off the top of my head. To reduce the free energy of the system. Anyway, I would laugh. But maybe your history class wouldn't. Okay, so will that also happen in perlite? Those same forces are at play in something like perlite or bainite. The lowest energy of cementite and alpha is still going to be balls of cementite. But now we have bigger pieces of cementite to start with. So if we heated perlite or bainite, we'd get something like spheroidite. Okay, so and you can see here, it's the second nose. What is this? That shape, that C shape to it, or the nose shape? What does that mean?
There's 2 processes at play.
There's 2 competing mechanisms. It's still a nucleation and growth of these things. We've got the nuclei there, and then growing, starting to form this shape, separating a lath from there. But now they're on the order of tens of microns. 3 orders of magnitude change in size difference of the particles. Good or bad? Bad. It's less strong anyway. I guess it depends on what we want. So tempered martensite is in general a very a very, well, I can't think of the word I'm looking for, but it's a microstructure that we want. You know, it's something that's very useful, like a useful microstructure, a useful material. Has useful properties, very strong, but still a little bit of toughness there. That's what we're going to make our kitchen knives out of, our swords. Not that we make swords, but you know, if we were going to. Tool steels. Okay. And so, what do you think about spheroidite? Do we like it as much? No, and I don't have the mechanical property information off the top of my head, but this is a very ductile steel, more so than pearlite. Okay? And so usually when we want to use something with steel, ductility is great, but we're really looking for that strength that we can get with steel. And so spheroidite is more something to be avoided. Yes?
How is it just something like austenite?
Okay, so an austenitic steel, what would that mean? What's austenite?
It hasn't layered or anything. It's one composition.
What's austenite? It's FCC iron, right, with some carbon in it. So that's what we started with. So an austenitic steel, and we'll often get them with austenitic stainless steels, is when we put enough alloying elements that we've stabilized austenite, the austenitic phase at room temperature. Right, we can change things. And so that's like something with a lot of nickel in it. So how does it compare with properties? It's much more ductile. But I should have thought of it. It was hard for me to find like information on mechanical properties of spheroidite because it's not something that's used. Like if I want the mechanical properties of a 1018 steel, it's all in a database for me. But if you want to find out, I can ask somebody who knows. Or spend more time than 2 minutes trying to find out. Okay, so just good to know that, you know, if you heat pearlite or bainite, this could happen. This is what all microstructures want to do. If we've got one phase and another, same thing why we have bubbles. Why do we have bubbles in boiling water? Why are they bubble shaped? Right, that spherical shape reduces the free energy. It's less perfect in solids because there's, you know, volume changes or phase change, and things are a little bit less easy to get perfectly shaped because the microstructure is not as fluid as in a fluid. But any questions about this in general? So what I want you to know, I want you to be able to look at or know what these microstructures are. If I gave you a micrograph, tell me which one is which. You'll see martensite. What separates martensite out is, and I apologize, there aren't micron bars on these images. They're all about, well, no, they're not about the same size. The two pearlite ones are, the bainite's much higher magnification, the spheroidite is a little bit lower magnification than the pearlite ones. But anyway, martensite is this, I call it like a basket weaver, you know, just completely disordered needles, not in any specific direction. They're not growing together, okay? That's how you can tell what martensite is. Tempered martensite, the size scale, it looks very similar to spheroidite. Why, so I said this was an SEM image, and this is an optical image. That's why the color of the particle separates out. With an optical image, we have to etch it to get the different phases to show up differently, which we'll talk about in corrosion. It's very cool. Corrosion for good. Used for good purposes instead of evil. And then an SEM image, the phase, the contrast of the phases, light versus dark, and what's what, is going to be very different because you're using electrons to image with instead of light. Any questions about this? And so we see, when we go back to the questions you guys did, we looked at ordering the microstructures. A lot of you did very well on them, okay? If I just gave you 3 microstructures, could you order them? Bainite, coarse pearlite, martensite. Well, what's the hardest there? Martensite. What's the weakest? Pearlite, right? Coarse pearlite especially. Lowest, to highest ductility? It's more ductile. Right? Again, make sure you're reading the question. I hate it when students miss a question on an exam because they didn't read it carefully. It makes my heart hurt. So, and I do try to like underline the important words that might be tricky on the exam. I'm not out to trick you, but... Okay, so from lowest to highest ductility, well, which one is the most ductile? Ceruttite. Which one's the least ductile? Martensite, very brittle microstructure. Lowest to highest strength. Which one's the strongest? Well, we've got, okay, which one's the least strong? Ceruttite, right? It's the useless one. Not useless, you know, but which one's the strongest? Between bainite and coarse perlite, which one's stronger? Bainite, right? The finer microstructure, funfetti cake. Whatever helps you remember it. Okay, and then we were looking at these cooling paths. So this was cooling path A. What kind of microstructure are we going to form? You just follow the path. When do you hit a red line? Right there. What is that red line for? That's a start line. Okay, so you're just following the yellow line, that path. That's the start of what? What's forming there? Bainite. Do we go to 100%?
Yeah.
Yep. So we have 100% bainite. Cooling path C. So follow the path. We hit a start line there. Do we go to 100%? Okay. What's starting to form there? Okay. Coarse perlite. How much do we form of that? We hit the 50% line. Okay. So now we have 50% coarse perlite. What's the other half at this point? Austenite, right? We're in a perlite and austenite region. So the rest is still gamma. It hasn't finished transforming. That image we had of the gamma grains and the perlites growing in from the sides, they only grew, the middle of the grains is still open, or still gamma, sorry. So then we quench it down, which I know this is a little weird, but I had trouble, I tend to draw them back that way. Start over. Okay, here we hit a start line. What's forming now? So our 50% austenite is starting to transform to bainite. Does it finish? Yep. So we have half perlite, half bainite. Sweet. So if I gave you a cooling path, either as a drawing or writing it out, could you tell me what kind of microstructure it would get? Or if I gave you different microstructures and said which one is going to give me half perlite and half bainite, could you pick it out? Okay, so summary. Our steel processing options. This is what I said at the beginning. We start with austenite. We heat it back into the austenite phase field. It erases the alpha and cementite microstructure. The carbon rediffuses into the hole. It takes some time, so we hold it up there. So now we just have FCC iron gamma with carbon inside. Then if we slowly cool it, or drop the temperature into the perlite region and hold it for a certain amount of time, we'll get perlite. If diffusion's high enough, or we cool it slowly enough, we'll get that equilibrium microconstituent, the alternating layers. If we have a moderate cool, we cool it a little bit faster, we'll still get alpha and cementite, but it'll be those needles or small grains of alpha with little precipitous rods of cementite inside. If we rapidly quench it, we don't allow diffusion to happen, we'll get martensite. So diffusionless transformation, we quench it to room temperature, we have 90 to 100% martensite. The rest is some retained austenites that keep that kind of, accommodate the shape change. And then we temper it. We don't want to use martensite as is, or at least not 100% martensite. We want to temper it. And so we can get combinations of these different microstructures. It doesn't have to be just one of the three. And that's one of the other things we talked about with the TTT diagrams. And so the complexity, the number of phases available. Okay, let's go back to what makes steel awesome. One, it's got a high melting point, high strength anyway. It's just plain iron, but it's very ductile. But when we alloy it with carbon, we have a ductile phase with a hard precipitate that naturally forms, not precipitate, a second hard phase. So now we have this combination that we can work out with chemistry of how much cementite do I want and how much alpha ferrite do I want. So that's the chemistry option. And we talked about that with the phase diagrams. How much proeutectoid alpha do I want? How much cementite? I can vary that with chemistry. And we're just talking about iron and carbon still. Then, when I vary the cooling rate, the arrangement of those two phases in 3 dimensions, the microconstituent or the microstructure, we have a lot of ability to engineer that. So it's the complexity is part of what makes steel so great. And each of these, so composition, cooling path, microstructure, each of them is a different material with different material properties. And so go ahead and look in the back of the text. It has, like, for steels, has a whole bunch of different kinds of steels, and it lists their mechanical properties. Modulus, yield strength. And you can compare them. Yeah.
When we have the tempered martensite and we heated it back up, now, do we have to cool it in a specific way to keep those martensite? So when it's had steel, quenched it, heated it back up, do I quench it again? Or would that shove it too much into the martensite inside? Or do I have to slow cool it?
Oh, would you quench it again after tempering it? You could quench it again because then you're locking in alpha and cementite microstructure. Okay, so he's asking, what's the role of quenching here? That if I'm quenching it, what that does is it locks in the microstructure, okay? So unless there's this diffusionless transformation that'll happen. So if I were quenching it, say, normally, I would lock in gamma. Well, not normally. So in, say, a copper-silver alloy. Okay? So let's say I was coming in at a let's say I cool it down into here, and then I quench it. I will lock in that alpha phase with a supersaturated concentration of B. Okay? So I won't have allowed the transformation of alpha to alpha and beta to happen. You're kind of subverting that natural transformation. And so in that case, there isn't a martensitic transformation. Does that make sense? So sometimes we'll just lock in the microstructure. Sometimes some materials will have this transformation. Otherwise, we're kind of locking that microstructure in. And I'll show you some examples of that as we go through the course, the lecture today. So it'll start to make more sense. Okay, so what do you need to know about phase transformations? You need to know nucleation and growth. How do they work? What's easier at which one? For TTT diagrams, I want you to know the shape. I want you to be able to work with them to predict microstructures or to design a heat treatment that would give you a certain microstructure. And so there's some reading of logarithmic time on there, right? I also want you to be able to identify a composition range. So if I gave you something where we're forming proeutectoid alpha, like as we talked about on Monday, can you tell me, okay, this is the type of, based on this is the TTT diagram that would go with this composition? For non-equilibrium microconstituents in steel, two big charts are this one. You get the processing options, and this one. So you get the arrangement of mechanical properties. And for all of these, we're trading strength for ductility and vice versa. Why? Why does that hold true for all of these? What if I had an aluminum alloy? Where would it fit in here? That would be comparing apples to oranges. Why is this comparing apples to apples in terms of this strength to ductility trade-off? They're all the same way?
They're all steel.
They're all steel, even more specific than that.
All the same composition.
They're all the same composition. Okay? So we've taken out the idea of specific solid solution strengthening, changing that at all, or changing the amount, the equilibrium amount of one phase or the other. We're just talking about comparing microstructures. Okay, now,